And I think we're ready to begin. So welcome everybody. Welcome to this week's ALS seminar. So I'll just give a brief introduction for people who are not familiar with how these things work. So the seminar is being recorded. But the only way you actually get recorded is if you ask a question during the talk, because we stop the recording after the talk, so this after the talk will not be recorded. We encourage people to keep your video on. If you want to ask a question during the talk, then please use the raise your hand feature in the participants menu in Zoom. As you've noticed, the chat is not really operational, but you can always send me a message. So if you see something strange happening that I need to react to, then please send me a message. And I think that's it. Yeah, I mean, we really do try to encourage questions. So we want to keep these things as interactive as possible. So if you have a question, please don't be afraid to put up your hand, and I'll interrupt Filippo and you can ask your question. That's something we actually really like. So anyway, without further ado, I think we'll get started. So it's my pleasure to introduce Filippo Bonchi from University of Pisa, who will talk about Functorial semantics from Lawvere to Carboni-Walters. Go ahead, Filippo.
Okay, thanks a lot for the introduction. I will show you a series of work that I've been doing with Dusko Pavlovich from the University of Hawaii, Pavel Sobocinski, that I guess you know since he just introduced me, and Jens Sieber, which just got his PhD degree and is now working as a postdoc in Pisa. These are a series of work that you can read in case you like the presentation. You see at the end the PhD thesis of Jens Sieber, logical completeness for string diagram. I will just show this at the very end of the talk. It would be more sort of introduction for his thesis. So our main motivation are algebra of relation. So there are different kinds of algebras of relation in all different souls. The one you see here is the positive fragment of the calculus of relation by Tarski of 41. So you can compose two relations R and S through the union, the intersection, or just take their relational composition. Or you have like as constants, you have the empty relation, the identity relation, or the top relation, which is the complete relation where every element is related to each other element. Here I'm fixing relation to be on the same set, let's say X. And then you can take reflexive and transitive closure of a relation or just the opposite of a relation. There are several fragments of this calculus which have been studied. There is the so-called Clini fragment, which consists of the first two rows, and the allegorical fragment, which consists of the second and third row. And okay, as usual in algebra, we are interested in some sort of laws which holds universally for all possible relations. Like, for instance, the distributivity of a relational composition over the union. And you see this is an equivalence, in the sense that this equivalence holds for all possible relation RST, while for the intersection, the distribution is only lax. So we have here an inclusion. Okay, and as always happen, one would like to have a set of basic axioms from which one would like to deduce, or a proof system, from which one would like to deduce all possible true statement. And for algebra of relation, and for many of these fragments, there are lots of results which are negative about the possibility of having a complete finite axiomatization. Here I list just a few of them, but really in literature there are many of them. And usually this proof of impossibility of having a complete axiomatization rely much on syntax. And so somehow on the chosen syntax. And so somehow our idea is that this syntax is what we should change. And let's say somehow we think that the usual way of writing things, so the usual one-dimensional syntax, which is made of 3, is good to denote a function. But as soon as we move to relation, we'll see that 3 are not so perfect, and we should rather use some sort of hypergraph. And we'll explain this using the tool of category theory. In particular, we'll see that the usual 3-base syntax correspond to Lawvere theories, and the semantics to Cartesian categories. While for relation, we have to consider Cartesian bicategories, which has been introduced by Carboni-Walters, and the corresponding syntactic counterpart is what we call Carboni-Walter theories. So in my talk, I will, so the idea of this talk is not really to explain you our result, but rather to give you an overall perspective on overall this topic. So I will not really show you any proof or any deep or any result, but rather how these things are related, and to introduce you to them. So I will start with a standard syntax and then Lawvere theory. So with this part here. Now we'll move to Cartesian categories and the so-called Functorial semantics, and then we'll move to relation. So the second half, the bottom part. Okay, let's start with the syntax. So one of the very first things that we learn when we study logic or computer science is that we usually write terms as strings, but we actually mean trees. For instance, when I write the expression y plus 3 times x plus y, I actually mean this tree here. So in this tree, the internal nodes represents the operation, times and plus. The number of son of each internal node is the arity of the operation. The leaves are constant, operation of arity 0, like in this case 3, or variable x and y. This allows us also to recall what is a signature. So it's just a set of operations equipped with an arity. For instance, in this case, times and plus as arity 2, and 3 is a constant with arity 0. Okay, the very first step that we have to do is to move from this one-dimensional syntax to string diagram. And to do this, we consider our tree. So this, we first write this like from left to right. So the leaf of the tree go on the left and the root go on the right. Then somehow we rename variable, assigning them an order. So we call, in this case, x, we call it x prime, and y, we call it x2. And then we want to somehow hide this variable and use some wiring technology to properly identify what variable. For instance, since x prime appears here, and so these are ordered, so x1 comes before x2, we need x1 to arrive here somehow, so we need this sort of wire crossing. And similarly, since x2 appears both as first argument of the first sum and the second argument of the second sum, so we need to identify this variable. So we need to say that this is the same variable x2, and we need this piece, which we call it copier. So here we have a copier and a wire crossing, which we call this a switch. We can think to this as circuits, and like with flow going from left to right. You see, we can think also this as arrow, where we have two on the left as source and one as the target. So somehow this is telling me the number of port of the circuit that the circuit says on the left, and the number of port that the circuit says on the right. Okay, there is one point here which is a bit, we should be a bit careful, and is in this assigning variable unordering. So this can always be done because we always assume the set of variable to be countable. So to have an isomorph, to be in one-to-one correspondence with natural numbers. So somehow this one-to-one correspondence already give us the corresponding natural number of the variable. But the way we do this is, for instance, here arbitrary. We could have done something different, like saying we go here and we give to x we go x prime, and to y we assign x3. And now here we will obtain a circuit with three ports on the left, because we have to say that the variable x2 doesn't appear. And this is what we use this for. We call this a discharger. So this is basically saying that the variable x2 doesn't appear in the term. Okay, so what we have used are string diagram. String diagram are basically a convenient notation for arrows in a symmetric monodal category. So we denote the composition of two arrows, the sequential composition, as putting the two corresponding circuits in sequence. The identity is just a wire. The tensor is just writing one on top of the other, and the identity over the unit of the tensor is just the empty diagram. And then we represent symmetries with this switch of wire. Okay, so we have that. So let's go back to term. Term form a symmetric monodal category, where the monoid of object is the monoid of natural number with addition and 0. So let's take, for instance, the term x1 plus x2. This is represented by this diagram, and this is an arrow which goes from 2 to 1. And let's consider also the term x1 plus x3. This is represented by this diagram, by these circuits, and these go from 1 to 1. So we can put them, combine them through the monodal product, and diagrammatically this means to stack one on top of the other, and this corresponds to the term x1 plus x plus 3 and x2 plus x3. You see here I have to somehow rename the variable of the second term, so not to confuse this x1 with this x1. These are really different. And what I obtain is an arrow which go from the circuits which go from 3 to 2. So you see here I'm summing up the source of the first arrow 1 with the source of the second arrow 2, and the target of the first arrow 1 with the target of the second arrow 1, which give me true. And you see this represent this pair of term x1 plus 3 and x2 plus x3. It's just this one. So somehow monodal product is just pairing. Now if I consider this term x1 times x2 is a term with source 2 and target 1. So since the source of this is equal to the target of the other, I can compose them in sequence, and I obtain an arrow from 3 to 1, which is the term x1 plus 3 times x2 plus x3. Okay. I guess these things are all standard, but I think it's important to recall them. They're important for what we are going to do. Okay, and yes, clearly composition, sequential composition is just substitution. Okay, it's important to recall to consider what are copying and discarding. These are also arrow from 1 to 2, and discarding is a copy is an arrow from 1 to 0. And it's interesting to see what kind of law they satisfy. So they form a commutative comonoid. So we have this form of associativity, which means, oh, sorry, I don't really care whether I copy twice the second here or if I copy here. The unit is much easier to understand if you think this is just saying, okay, if I copy and then I discard one of the two, then this is just equal to doing nothing. And then the commutativity say that if I copy and then I switch the two copy, this is actually equal to just copy. In the sense that I cannot distinguish between the copies that I'm doing. And the other law, which copying and discarding satisfies, that all arrows are comonoid homomorphism, which means that if I have some arrow and then I copy, then this is just equal to copying and then put the two arrows in the monoidal product. And similarly for discarding, if I have an arrow and then I discard, it's just equal to just discard. Okay, let me say here that here I'm writing this n, I mean n copies in tensor of the discharger, and when I write this, I mean n copy of this done in the obvious way. For instance, 2 is just equal to, and then I switch here. So actually, for every natural number n, I have an n version of copier and an n version of discharger. Okay. The nice thing of this law is that now I can take every diagram, every circuit, and then I can use this law to reduce it to a tree. And this actually explains me why the usual syntax are trees. So for instance, consider this term. So do you know what is this term? Do you have any guess? So this is just, so x1 is discarded, this is x2, and then I do x2 times x2. So I want to compose this with this. This is a tuple of term. So the first one is x3 plus, here I have x1, and this is x1 plus 3. So if I compose them, I just put the two circuits one next to the other, and I obtain this circuit here. And now I can apply the law of the discharger, which destroy the plus, and I arrive here, and also got this one here, and then I can apply the unit here and get rid of this copier, and also destroy the tree. What I end up into this diagram, and now here I have a copier followed by an arrow from 1 to 1, and I can copy it twice. So what I obtain here is the term x1 plus 3 times x1 plus 3. Okay, these allow us to explain what are Lawvere theories. So the monoid of object is the one of natural number with addition and 0, and the arrow are all the diagram which are generated by the following grammar. So I just take the identity of 0, the identity of 1, the switch. I compose arrow in sequence, in parallel. Then for every symbol of my signature with arity n, I introduce a box with n ports on the left and 1 on the right. And then I really need the copier and discharger. So I take term generated by this syntax and I quotient them by the law of copying and discharging, and then obtain my Lawvere theory. Okay, I can also take Lawvere theory for some algebraic theory where I have some set of axioms. In this case, I have also to quotient with respect to these axioms. So these axioms are just pair of arrows, like s equal to t. For instance, I can have x plus x equal to 0. You see here that copying is fundamental to express x plus x, but also to express 0, I need to use the discharger. Okay, these also allow us to introduce the semantic sides. So a Cartesian theory is a symmetric monoidal theory where every object at X is equipped with a comonoid, so a copier for every object and a discharger for every object, such that all comonoid are, all arrow are comonoid homomorphism, exactly as holds for terms. Let's see an example of Cartesian category. Lawvere theory for sure are a Cartesian category. I said here the object are the natural number, and for every natural number I have copier and discharger, and all the law holds. And the other standard example is a set, where the monoidal product is the Cartesian product. And the discharger, as you expect, is the diagonal, which go from x to x times x. And the discharger is the only function from x to 1. Okay, so next step is to define what is a Cartesian functor. Is exactly what you expect. Cartesian functor between two Cartesian categories is just a functor that, symmetric monoidal functor that preserves the comonoid. So let's say, let's take as an example a functor from a Lawvere theory to set. And you see, here we are forced to map the plus into the Cartesian product, the 0 into the 1. And then basically, this, for the object, they are all determined by where 1 is mapped. So let's say 1 is mapped to x, then n would be mapped. Then n would be mapped into x times x times x n times. Sorry. Okay, then the interpretation over the comonoid is fixed by this. And so the only other degree of freedom that we have in defining a functor is over the symbol of the signature, over this gadget here. We have to choose where to map this, which means exactly to choose a function f which go from x up to the n to x for every symbol f with arity n. So let's recap. A symmetric monoidal functor between a Lawvere theory and set is uniquely determined by the choice of where we map 1, so a set x, and function f from xn to x for every function, for every object of the signature. So these are exactly models of the algebraic theory sigma e. So a set x and an operation for each symbol. The fact that it's a functor also ensures that the axiom in E are satisfied. So this is somehow the crucial point beyond Functorial semantics. So algebras or models of the theory are in one-to-one correspondence with functors, with Cartesian functor. So let's see, be a Cartesian category, a sigma E algebra, or a sigma E model over C is a Cartesian functor M from the Lawvere theory, corresponding to the theory sigma E, to the Cartesian category C. And an homomorphism is just a natural transformation between two functors. Okay, and these somehow give us this what we call the love triangle. So we have a correspondence between Cartesian categories and trees given by the Lawvere theory. I show you, and the kind of logic that we can use to express the Lawvere theory is just equational logic. And so we have these three sides which corresponds in a precise way. I will show you later that this also for relation if you use the proper things, the proper setting, the proper algebraic setting. Okay, so let's now move to relation. So I show you these and these. So now we move to this part on, especially on the semantics now on relation. Okay. The very first observation is that the category of sets and relation is Cartesian, but the categorical product coincides with the coproduct, so with disjoint union. And for this reason, Functorial semantics, as intended by Lawvere, is quite meaningless, in the sense that times would be mapped into somethings which go from x plus x to x, while for us it's really fundamental to have the Cartesian product, not the disjoint union. So we want the monodal product to be the Cartesian product, and so we consider the symmetric monodal category rel with the monodal product given by the Cartesian product x and the unit 1. So in here, in this category, the monodal product is just given by the Cartesian product of relation. So these basically are the relation that we obtain is the relation of pair x1, x2 in pairs with y1, y2, such that x1 is in relation with y1 and x2 is in relation, sorry, here is a typo, is in relation S with y2. And composition is as usual relational composition as you expect, as you can see here. Okay. We also have that every set is equipped with a comonoid. So every object of this category is equipped with the comonoid, exactly the same comonoid that we have in set, since every function is a relation. But this is what makes this symmetric monodal category fail to be a Cartesian category, is that these not all relations are comonoid homomorphism. This is really the crucial point. What does it mean to be comonoid homomorphism? Let's consider this first one here. So this relation here corresponds to this one. So here you have x and then two copies of the same y, such that x is in relation with y, while in the relation that you obtain here, you have an x here and a y prime and a y2, such that x is in relation with y prime and x is in relation with y2. So clearly the inclusion from here to here holds, but not the other way around. For instance, if you take R to be AB, AC, and X and Y to be the same set ABC, then here you would obtain both AB, you would obtain also ABC, which is not possible to have it here, because here this is the copier, so all the value here should be the same. So here you will only have ABB and ACC. And similarly, this not every relation is natural with respect to the discharger. You see this relation on the right is just the full set X, and the relation on the left is given by the set of all x, such that there exists a y for which x is in relation with y. So this inclusion doesn't hold, but the other inclusion in the other direction always holds. And this is what allows us to define Cartesian bicategories. So a Cartesian bicategory is a symmetric model category where every object x is equipped with a comonoid, which we draw like this, such that, so every arrow is a lax comonoid homomorphism. So these two inclusion holds. And then we have that this copier and discharger have rights adjoint. Having right adjoint means that this inclusion holds. Basically, this is the eta of one adjunction. This is the co-unit of the other adjunction, of the same adjunction, and this is the unit of the other adjunction, and this is the co-unit of the other adjunction. And okay, if you think in terms of set relation, this is rather intuitive. This, for instance, this is just the relation which say that all the value in the 4 ports have to be exactly the same, while this is the relation which say that the value on the first port, on the top ports have to be the same, and this is the relation which say that the value on the bottom port have to be the same. Okay, and then we require that the Frobenius law holds, which is this one. Okay, this defines a Cartesian bicategory. Okay, and for sure, just let me say that this can be thought, while we thought this as copier, in REL we can think this as an equality test, and to this as an existential quantifier. Okay. Sorry, here I did a mess. Yes. Okay. I just want to say, okay, the category of set of relation is clearly a Cartesian bicategory. Is our main example, and here I want to show you something which I find quite interesting. So you see, these are the inclusions that do not hold. I just show you. But this actually holds only if the relation R is a single valued. So this means that for all x, there exists at most a y, such that x is in relation with y, or univalent, single valued or univalent. While for totality, so this holds if and only if the relation is total, which means that for all x, there exists at least one y, such that x is in relation with y. But we can also consider the analogous inclusion with the equality test, the existential quantifier. And if we do so, we obtain the notion of injective relation and surjective relation. You see, the only difference is that here we are switching. So here we are saying for all x there exists at most one y. Here we are saying for all y there existed at most one x. And similarly for total and injective. We have a complete duality here. We go from at most to at least, and here we move from x to y. Okay, so let's say now what is a Carboni-Walter theory. It's basically the same as a Lawvere theory, but for Cartesian bicategory rather than Cartesian categories. So the arrow, the monoid of object is the natural number, and the arrow are generated by this grammar. And so in addition to copier and discharger, we have the equality test and the existential quantifier. And these all are quotiented by the law of Cartesian bicategories. And the axiom in E. Let me say something about the axiom in E. So these are not equation anymore, but are rather inequation for precise reason, which we'll maybe see later if I have time. And also let me say something else. Symbol in sigma, you see here, they don't only have a narity, but they also have a coarity. The point is that in having symbol with a coarity in the Cartesian setting is totally pointless, because I can always decompose one such symbol like this. I call this F1 and this F2, and I obtain exactly the same. While here it's meaningful and actually it's important. Okay, now the functorial semantics for relation. We take C to be a Cartesian bicategory, and we say that a sigma I algebra over C is just a Cartesian bifunctor, which go from the Carboni-Walters category to C. And homomorphism is a lax natural transformation. I will not really show you homomorphism. So let's see some example. I can take as a signature having only one symbol R with arity 1 and coarity 1, and I can impose as axiom this inequation. So this say if I compose R with itself is included into R, reflexivity say that the identity is included into R, and symmetry that R is included into R op. Actually, to express R op, I can use the copulent discharger and the quality test and the existential quantifier to reverse the relation, to obtain the opposite relation. Indeed, every Cartesian bicategory is a compact closed category. So we can define op like this. And okay, we take these are our axiom in I, and a sigma I algebra over Rel is given by a set X and exactly a relation R over X which satisfy the tree, so which is an equivalence relation. I can also express antisymmetry. You see here I use the copier and then the quality test. In this way, I say R included into intersected with R op is included into the identity. So actually, I can define every intersection. If I have R and us, I can intersect them always in this way. Okay, and sigma algebra over Rel is just a partial order, so a relation which satisfies the tree here. So now let's take the signature plus and 0, and I can express associativity, unit, and commutativity. I would like to define in this way the theory of monoids. But if I really want to have monoids, I have to impose that plus and 0 are total, and totality is expressed exactly in this way, and that they are single valued. And this is expressed exactly like this. Okay, once I do this, I need to add all these axioms, and now here I really obtain a commutative monoid. But I can do also something more. I can do, for instance, non-negative monoid. Let's consider this axiom. You see here I'm saying, here I have the term x plus y equal to 0, and this should be included into, this is just x equals 0, and this is y equals 0. So basically, I'm imposing that this implication holds, and what I obtain, like this, an algebra for this theory, is a non-negative monoid. So you see, this is clearly much more expressive than what we can express with usual equational logic and what we can express with Lawvere theory. So how expressive is the language of Carboni-Walter theories? So for sure, it's more expressive than allegories. We can express allegories like this. Oh, sorry for this. And okay, so we have composition and identity. You can be expressed like this. Intersection, I show you. the total relation is just this one, and the opposite I already showed you. And actually, we can express it. You can express exactly as much as regular logic, or this is also called the language of conjunctive query from the theory of the database. So we look at a relation with n argument as an arrow from n to 0. And then we can express the equality x0 equal to x1 just like this. The existential quantification is done by using the existential quantifier. And then the conjunction is just using the copier. And so, okay, and they have exactly the same expressive power. This is exactly the corresponding of regular logic. And we can also use the axiom of Cartesian bicategory to make proofs. For instance, let's take the theory of monoids, and let's define these circuits, this plus reverse, just as plus op. I already told you what is op. And I can prove things like this, for instance, that the identity over 2 is smaller or equal than this plus composed with this opposite, and also this other one here. And from this, for instance, I can deduce some sort of Lax-Frobenius law. So I can use A here, and I can add here in place of the identity. I can put the 2 copy here of these 2. I can put them here, and then now I can use associativity to switch these and these, so that I obtain this string diagram here. And then finally, I can use B to get rid of this and put an identity here and obtain this one. So it's interesting to see that only this Frobenius law only holds laxly. To have the other inclusion, one needs to have at least a ring.
Sorry, Filippo.
Yeah, I've basically finished.
Jamie Vickery has a question.
Yes. Yeah.
Jamie, go ahead.
Yeah.
Thanks, Pavel. Thanks, Filippo. So suppose that so in these proofs, right, you're using the fact that you've got a certain equational theory that you've presented.
Yeah.
And it's a presentation of a Carboni-Walters theory.
Yeah.
But suppose instead I just considered it as a presentation of a 2 category, or like a finitely presented bicategory or something.
Okay.
Couldn't I make just the same arguments? I don't really see why. I mean, certainly, for example, this proof along the bottom, right? I could just add these things A and B as 2-dimensional generators, and then I work in the free bicategory or free 2 category, if you like, generated by the signature. And then I could give this proof at the bottom. I'm not really seeing what the infrastructure of the Carboni-Walters theory is buying us.
Okay, let me say let me show you next slides where I'm proving A and B.
Oh, so A and B are not in your signature, as it were.
No, these are derived laws, and okay. I didn't prove them. I didn't prove them. So the theory that I'm considering here is just the theory of commutative monoids. If I want to show you why A and B holds, I will show you in the next slides.
Okay. Sorry
for this confusion. The reason why I show them later on is that like these follow from a more general fact, and is that if R is a single valued, so if this inequation holds, and I imposed this inequation in my theory of commutative monoid, then R op composed with R is always included into the identity, and this holds in any Cartesian bicategory in every Carboni-Walter theory. So why like this? So I have R op composed with R. So I write R op like this, and I compose it with R. Now I push R a bit here, and since these holds, now I can push the R inside here and get rid of this because of the law of Cartesian bicategory. So what I obtain is just this, which is just the snake, which is the identity. And the same, so this is exactly A. right? No, this is B. This is what I call B. If in place of R you take plus, this is B. If in place of R you take plus. And while this is A, this is A. And so this say more generally that if R is total, then R composed with R op is greater, includes the identity. And the proof is analogous, more or less the same.
But this is only for some R which is single valued, right? Not for an arbitrary.
This holds for any R which is single valued and which is total. And I have imposed, I mean this, and I have imposed this, sorry, in my theory of, you see here, in my theory of for.
But in the theory, how do you say that it's single? Oh, right. So you, right.
I can express this in this way. So you see, this inclusion always holds. So here, actually, what I'm imposing is this one, and here is the same. This inclusion always holds. So what I'm imposing here is this, and what I'm imposing here is this, and same here for totality. So I need to add this axiom to my theory I. So I can distinguish between functions and relation just by using these two tricks. And this is what you always do in first order logic, right? You say this symbols denote functions and these symbols denote relation. Here you don't really make any difference. You just impose some axioms, and that's all. Sorry, I mean in first order logic you say either function symbol or predicate symbol, but you can do exactly the same here.
Sure. I mean, the point is that this setup is not purely geometrical, right? You're not only using the axioms that you give, say on this slide, you're also using things that you can deduce that are special about the algebra of relations, right?
No, I mean, I can prove this, all these, I can prove this geometrically. It's just that I wanted to show you. I mean, I can do the same proof, but
sure,
that I've done here, but using this plus here. And when then now I use totality here, I will use an axiom in I. Right?
Okay, but my point is, if you are just working purely geometrically, then I don't see why you need to work with the infrastructure of Carboni-Walters theories. Why not just say I have a free 2 category on some signature? Maybe we could talk about it afterwards. Maybe it's not clear what I'm asking.
Yeah, I think this discussion is probably best if we take it offline because it's we've been going on for a while. So Filippo.
No, the point is that this really give you I mean, you see here I'm really using the axioms of Cartesian bicategories for making all this deduction. And the main point is that we have completeness. This is the overall point. So if I can deduce something through my axiom, then this holds for all possible functors. Okay, this is obvious, this is soundness, but completeness is what really cares. So if an inclusion holds for all possible in all possible model, then this can be deduced by my system of axioms. And this somehow give us another love triangle, where we have now in place of logic, in place of equational logic, we have regular logic. We show you these are exactly the same. In place of Cartesian category, we have Cartesian bicategories. And in place of trees, we have hypergraph. I haven't shown you this in detail, but there is a close, yes, there is an isomorphism between the string diagram. I can write modulo, the axiom of Cartesian bicategory, and what we call cospans of hypergraph. And okay, something else which is kind of interesting is that this correspondence between regular logic and hypergraph was already noticed in a very beautiful paper by Chandra and Merlin, which basically inspired most of this triangle. Okay, and that's basically all and what I want to say. Thanks a lot.
Okay, thank you very much, Filippo. So before we take questions, I think we'll unmute ourselves. I think I can't, for some reason, I cannot see an unmute button. So can people try to unmute themselves? Yes, good. Okay, so let's thank Filippo.
Thanks.
Okay, now I'm going to mute all. And Filippo, you can unmute yourself. So are there any questions? I have a couple of questions from the chat, but maybe if you would like to ask a question, please raise your hand. Filippo, can you unmute yourself? Perfect. Okay. So we have a question from Damien Pus. Damien, please go ahead.
Hi, Filippo. Thanks for the talk. It was really great. I have this question about this definition of totality or single valued. On this equivalences on the last but one slide, I think.
Filippo, you're still muted. You need to unmute yourself on the computer.
Okay.
Now we can hear you.
Yeah, so are these if and only if, by chance?
Yes, they are if and only if, sorry. Since I need them for the other proof, I only take this direction, but the correspondence is one-to-one, yes. They are if and only if.
Yeah, because people I mean, doing algebraic proofs in relational algebra, they tend to use the definitions on the right for totality and
yeah, indeed. You can take both as definition, yes. But we take this other as definition because it's somehow it makes more clear the role of copier and discharger, which we think is really the fundamental part somehow. But yes, this is the other definition. So it's an if and only if.
Okay, Marino, I think you're unmuted. So Marino Mikulan has a question.
Yeah. Thank you, Filippo. Nice talk. Really enjoyed it. I have a question concerning value generalizations. Actually, I was wondering if it is possible to figure out some kind of balanced monoidal bicategories in order to get some traced monoidal bicategories in the style of Joyard street verity, in order to get feedbacks on this level.
Yes, so actually we arrived to Cartesian bicategory with Pavel because we were working on a signal flow graph. So we have done this algebra of signal flow graph, and then there you really have feedback with arrays. So these are really trace monoidal category in the sense of Joyard, and the cool thing is that this we didn't realize immediately, but at some point we started to look at the two-dimensional structure, and then we realized that all these inclusions were holding and that we had a Cartesian bicategory. And actually, in that case, we even have an abelian bicategory, but really. And yes, so we can do all kind of feedbacks with this. This is given by the black structure.
Okay, thank you.
And yes, I think Bob Walter used a lot of this for doing this kind of stuff. Probably yes in this. Thank you, Marino.
So we have another question from Paul Taylor. Paul, can you unmute yourself, please? Paul, can you hear me?
Yeah, I'm trying.
Please go ahead. Hey, you're muted again. We heard you for a second or so. You seem to be muted again. Hello, Paul. Okay, so we seem to be having some technical issues. Maybe we'll come back to Paul. I've got a question in the chat from Zanzi. Filippo, can you tell us about what the free thing is? So somehow the diagrammatic approach, so the free Lawvere theory, Lawvere theory on the empty signature can be characterized nicely diagrammatically using this kind of approach. Can you say something similar for Cartesian bicategories?
Yes, so the free one is I can characterize the free one as a cospans of functions and infinite set. But what was the Jens, do you remember there was there was something for the free one? I'm confused now.
Hi everyone. Yeah, so the free one on one object is cospans of finite sets, where you take the ordering. It's this existence of a morphism thing. So do you mean free one on an object or free one on
Free one on an object.
signature?
Yeah, on one object, on one object. Yeah, it's cospans. Yeah,
so
and then
that's
we need...
given by cospans of finite sets. Yeah.
Yeah. Okay.
Okay, thank you. So we have a question from Paul. I think, Paul, now we can hear you.
Sorry about the confusion with my mute button. No, just a comment about terminology. Please, 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 can we retire the word Cartesian? Because it has far too many uses in mathematics. And in the case of Cartesian categories, the meaning is ambiguous.
Yes.
In this context, it means a category of finite products. Peter Fried said that it was a category with finite limits, that is, say, including equalizers and pullbacks. So let's call them finite product theories
Yeah.
instead. And so the comment applies pretty much to many category theory talks. If you're using the word Cartesian, please think of another word.
Yes, I
But it was a very good talk. You've as it were embedded a lot of very old material into recent notation, and I suspect that Jamie is right in saying that generalization is can be done from this point to probably to higher dimensions. So it's a nice talk. Thank you very much.
thanks a lot, Paul.
So I think you have a question from Carlos. Carlos, I think you're muted. Go ahead.
Thanks, Pavel. Hi, Filippo.
Hi.
I wonder, when you started the talk, you started like the motivation was to provide the categorical semantics for relational algebra, and you used all this wiring technology, as you call it. I like the wording. For representing relational terms in two dimensions. I wonder why didn't you use, this wiring technology doesn't have any relational counterpart. So it is not part of the algebraic behavior. It is being added just to provide the categorical semantics. And I wonder why didn't you start it with fork algebras? Fork algebras has this relational behavior. So you can structure your domain to link stuff. It is an extension of relational algebra with just one operator called fork. And the good thing about them is that they are representable in a proper class of algebras. So it is in some sense set theoretical. The semantics is set theoretical. It is finitely axiomatizable. The axiomatization is equational, fully equational, and it can be extended with closure. Also with an almost equational, it is you need an infinitary rule, of course, but you have a complete axiomatization for the closure too. So do you have you thought about that?
So I must say it's the first time I heard about this fork algebras, but I'm really curious. What is exactly the fork doing?
The fork serves the purpose of structuring the domain. So you have an injective operation that allows you to, let's say, relate something like this. I'm drawing here quickly. So you have a star, which is injective. Sorry for the improvisation. So you have, if you have relations R and S, it allows you to do this. So you have an injective operation, which is the star, and it relates X with the star between the two elements Y and Z. So the good thing about that, it was devised just for providing representability for relational algebras, a long-standing problem, as you told at the beginning. It is one of the problems stated by Tarski in 41's paper. So this allows you to provide full representability over a proper class of relational algebras.
But this seems to go quite in the direction of what we are doing, in the sense that...
Yes, exactly.
Yeah.
That's the reason why I thought about it, because these kind of algebras have the relational behavior that you are modeling, that you could be interpreting as the wiring technology, that for relational algebra do not explain any relational behavior, but for fork algebra, it is explaining a very specific behavior that the class of algebras has. So maybe just to look at it with more time.
This is definitely something I should check.
And if I have one more second, do you have have you seen the work on graphical calculi for different fragments of relational algebra of the group of this Brazilian logician, Paulo Veloso? They did quite some work on graphical calculi for relational fragments.
No, this is very interesting. How is called, the guy?
The guy is called Paulo Veloso, but most of the work was done by Petruccio Viana and Renata de Freitas. I can send you some links, and maybe I have some of the work they did, but I have to check.
Thanks a lot. There are for sure deep relation.
Paulo Veloso was the one that invented, let's say, extended Tarski's relational algebra with fork.
I see.
That later was taken by Nemeti and Andreka, and all of them studied the meta-theoretical properties for a while, like representability, non-representability of certain interpretations of star, things like that.
I think we're going to have a lot to discuss after the talk, so this is all really interesting. But we have one final question from Sanjeeva Prasad, so please go ahead, Sanjeeva.
Thanks. Hi, Filippo. That was a great talk, and thank you for the reminder of the regular logic to hypergraph paper by Chandra and Merlin. You gave this lovely, naturality for homomorphisms. What's the corresponding notion in these bicategories, or in the these regular logics and so on? In this framework, what is the corresponding notion for homomorph? What's the intuition?
Can you repeat the question?
So you talked about the notion of homomorphisms for sigma algebras in terms of the naturality. What is that? Does that carry over here as well? Morphisms between the relations.
Morphism between the models, you mean?
Yes, that's right. That's right.
So just let me. Here.
Right.
Yes.
Okay.
So this is something that I mean, you obtain exactly what you expect, in the sense that morphism are.
Okay, they lax natural transformation. Okay.
Need to be lax natural transformation, and
okay.
And the intuition is that morphism turn out to be functions between models, between algebras, which has to satisfy which have to preserve the relational structure.
Okay.
And this is kind of forced. This definition is really forced to. Is really forced by the fact that every arrow must be a comonoid homomorphism.
Mm-hmm.
Because if you take natural transformation, if you force them to be not lax, but really natural transformation, then you would obtain as homomorphism only isomorphism.
Okay.
And for sure, you don't want this.
Yeah. Okay. I think that pretty much exactly answers what I was wondering.
Thanks a lot. Thanks a lot.
Fantastic. So thank you very much, Filippo. Can we try and unmute ourselves and clap? So I'll just give people a couple of seconds to unmute yourself. I don't seem to have the button unmute all anymore. So if you can unmute yourself, please go ahead, and let's thank Filippo. Okay, so thank you very much. I'm going to now stop the video, stop the recording.